Hello. So in this video I want to talk about an algorithm for how to find the inverse of a matrix. So let's just recall that if I have a square matrix, if A is a square matrix, then an inverse of A is a matrix B such that A times B is the identity. And of course, since we're talking about n by n matrices, it's the n by n identity matrix. So let's say that you have an n by n matrix A, inverse of A is, okay, it needs to be an n by n matrix B such that A times B is the n by n identity matrix. That's the definition of the inverse of a matrix. And there are a few things to note about this is that depending on the book you're reading, okay, you might also have this additional requirement that B times A is the identity matrix also. So it's A times B is the identity matrix and B times A is the identity matrix. But there's a theorem that says that, so there's a theorem that if A times B is the identity matrix, then B times A is also the identity matrix. That's a theorem that, okay, in this video anyway, we're not going to prove. So you really only need, and it's also vice versa. If B times A is the identity matrix, then A times B is also the identity matrix, if we're talking about square matrices. So actually, when you're checking if a matrix is an inverse, you only need to multiply it on one side. And if you get the identity matrix, then you know that if you multiply it on the other side, you'll also get the identity matrix. Of course, in general, A times B is not equal to B times A. So there's something special about the identity matrix that makes this work. And yeah, okay, so that's the definition of the inverse of a matrix. And so the question is, if you have a matrix A, a square matrix, how do you tell if it even has an inverse? And if it does have an inverse, how do you find it? So that's the question we'll talk about. So given an n by n matrix A, how do you know if A is invertible, and if so, how to find its inverse? One thing I'm sort of sweeping under the rug is that from the definition, technically, speaking, right, there could be more than one inverse. I mean, strictly speaking from the definition, it just says n inverse of A is a matrix B. But in advance, I didn't say that there couldn't be more than one B. I mean, there could be like lots of different matrices such that when you do A times that matrix, you get the identity matrix. But it turns out that, okay, this is another theorem, is that there's only one possible matrix that will do it, and that would be the inverse. Okay, so if there is such a B at all, there's only one of them, and so we can call that matrix B the symbol A inverse. So that's the symbol for it. Okay, maybe I should write that down. There's another theorem that says there is at most one inverse of a matrix A. Okay, let's just take these for granted because this video is about how to find the inverse, not the general theory behind this kind of thing. Okay, hopefully I'll have time to make another video about this, about how you know these theorems are true, but let's just take this for granted. So if A is invertible, well, the question is, how do you know if A is invertible, and how do you find its inverse if it is invertible? Well, the idea behind this problem that we can solve is, okay, let's just recall that if you have this matrix A, so suppose this is like a review. Suppose that you have two vectors b1 and b2 in Rn. Well, then we can solve a times x equals b1 and a times x equals b2 by looking at the augmented matrices, by forming augmented matrices. So maybe a times x1 is b1 and a times x2 is b2, by forming an augmented matrix where you take A and then you kind of append this vector b1 to it, right? And then, I mean, obviously you would just do the same thing for b2 and then you would solve for it. You would row reduce this matrix until A is in echelon form, and then once A is in echelon form or better, reduced row echelon form, and then once it's in reduced row echelon form, you really can just see what all the solutions to AX equals B are. Now the idea is that, so the key idea for finding the inverse of A is that when we row reduce, suppose that you have these two systems of equations that you're trying to solve. You have two of them, but you have the same coefficient matrix A. The idea is that when we row reduce, so let's just call this M1 and let's just call this M2. These augmented matrices, when you row reduce M1 and M2, you do the same, we do the same row operations to A. Okay, let's just look at an example. So let's say that you just have some matrix, some simple 2 by 2 matrix A, which is the first row is 1, 2, and the second row is 3, 4. And you have B1, which is 0, 2, and you have B2, which is 3, 1. Okay? So let's say that you want to solve AX1 is B1 and AX2 is B2. So we're solving for x1 and x2. Well, what we would do is we would set up an augmented matrix oh, 0, 2, and then when we work with this augmented matrix and row reduce it so that the coefficient matrix is in echelon form, we can solve the system. So what we would do here is we would take row 2 and subtract 3 times row 1. So then, okay, I'll just write down what you get. You get this. And then the next step is to divide row 2 by negative 2. And so you get this. And then to get it into reduced row echelon form, you take row 1 and subtract 2 row 1. You take row 1 and you subtract 2 row 2. So that will give you this 2 by 2 identity matrix and then this column on the right. And so that tells you that x1 is going to be 2, negative 1. Okay, easy. And then when you do B2, you just do the same process. The only difference is the column on the right, right? But this matrix is the same. I mean, you're row reducing this matrix, you do the same steps. So you replace row 2 by row 2 minus 3 row 1, and that will give you this. And then you divide row 2 by negative 2, and then you replace row 2 by you replace row 1 by row 1 minus 2 row 2, and that will give you, again, the identity matrix, and then negative 5, 4. So if you just look at what we did, right, here, and here, and And here, when you look at what happened to the the coefficient matrix, it was like this, and then it became that, and then it became that, and then it became that. And it's the exact same thing for the second one when you had the B2, because the only difference between the first one and the second one was the B1 and the B2 were different, right? And so you get a different, of course, you're going to get a different x2, so x2 is going to be negative 5, 4. But what we did to the A part was exactly the same. So what we could do to save time is we can augment A by, before we had one column, augment A by B1, and then you augment A by B2, but we can augment A by 2 columns. We can augment A by B1 and B2. Let me explain how this works. So what you would do instead of doing what we did, which is like doing the same thing twice, is you could take your A and then augment it by B1 and then augment it by B2. So you have that. And then you row reduce this augmented matrix. And what you do if you do that, well, it's exactly the same, right? You're just row reducing this matrix. So you do row 2 goes to row 2 minus 3 row 1, and then that will give you this. And then you divide row 2 by negative 2, and that will give you this. And then you change row 1 to row 1 minus 2 row 2, and that will give you this. And now you see that x1 is this column and x2 is that column, right? Okay, now let's apply what we just learned to the problem of finding inverses. So going back to finding A inverse, okay, what we're trying to do is we're trying to come up with a matrix B such that A times B is the n by n identity matrix. Well, let's say that you have B, and let's say that its columns are x1 through xn. What this should equal is A times that matrix should be the n by n identity matrix. Well, the columns are E1 through En. So what we need to have happen is A times x1 needs to equal E1, A times x2 must be equal to E2, all the way to A times xn must equal En. Because remember, when you multiply a matrix by another matrix, you multiply the matrix by the columns. Right, A times this matrix, A times the first column of B will equal the first column of the product. A times the nth column of B will equal the nth column of the product. That was how we defined the product of two matrices. How do I make this go back? Okay, so A times x1 will equal E1, A times x2 equals E2, all the way to A times xn equals En. What we need is x1, x2, up to xn that satisfies all these systems of equations, right? This first equation, we can think of it as a system of equations. And so we have n systems of equations, and we just learned how to handle a bunch of systems of equations when you have the same coefficient matrix A. What you can do is you can augment. So we just learned that we can augment A not by one column, but by all the columns E1 through En, and then row reduce. So this is just the case that we had before, except your B1 is your E1 and your B2 is E2, right? So let's just look at an example. So basically what we do is we take our augmented matrix, which is formed by A, and then the n by n identity matrix, I. So let's look at an example. Find A inverse if it exists for A equals 1, 2, 3, 4. Well, what we would do is we augment this matrix by the identity matrix, and then we row reduce. So we already did this. We change row 2 to row 2 minus 3 row 1, and that gives you, I'm just going to write down what we get because I'm assuming we all know how to do this. You get this, and then you divide row 2 by -2, so you're going to get this. And then finally, the last step is row 1 minus 2 row 2. So you get this. And now what did we learn from this? We learned that A times this column is going to equal 1, 0. And A times this column is going to equal 0, 1. Therefore, this matrix here, that's the inverse. So A inverse is this matrix. -2, 1, 3 halves, -1 half. Okay? And the fact that we were able to solve this shows that A inverse exists, right? Because we were able to find the x1 through xn that made A times xi equal ei for all I. In other words, we were able to come up with the matrix B such that A times B is that identity matrix. So if you had something where you weren't able to solve this, then A would not be invertible, right? So if the system is inconsistent, then A is not invertible. And that's actually something that if you're thinking about inverses, right, you want Ax equals 0 to have only the trivial solution, and so you need n pivots. So if the echelon form of A has n pivots, then A is invertible, and you're able to solve the system. Otherwise, A is not invertible. I mean, what will happen? Let's see what will happen if you had something like A equals 1, 2, 3, 6. So we can see that A is not invertible because for instance, the second column is a scalar multiple of the first column. Well, what happens if you try to do the same process before? Right? If you're able to solve this kind of augmented system, A times, see, this is like A times X is the identity matrix instead of A times X is the vector. If you're able to solve for the matrix X, well, we call it B, then that will be the inverse. And if you can't solve for it, then the matrix inverse doesn't exist. So let's see what happens if you row reduce. Well, we're gonna replace row 2 by row 2 minus 3 row 1, and that will give you a row of zeros here, and then you're going to get -3 here and 1 here. Well, obviously you're not going to be able, you're not going to be able to solve. Like, you can't solve this matrix times a vector equals 1, -3 because of this 0 row, right? And so we see that A is not invertible. So since echelon form of A has 0 row, A is not invertible. So sort of along the way, by doing this algorithm, you can figure out that A, in this case, does not have an inverse. Okay? So, this algorithm, you don't have to know in advance that A is invertible. You can figure out whether or not A is invertible, because by doing the algorithm, you're going to get A into echelon form, and then you can see if the echelon form has a 0 row or not. But this video is more about understanding why this process works. And one way to think about why it works, this is probably the easiest way of thinking about it, is this fact that when you have A times x1 equals b1 and A times x2 equals b2, instead of taking two augmented matrices and then solving for x1 and x2 separately, what you can do is you can augment A by both columns b1 and b2, and then when you row reduce, you're going to get both columns x1 and x2. And same thing for, if you had b1 through bn, right? You're going to get x1 through xn. And then going back to the problem of the inverse, this issue of finding a b such that A times b is the n by n identity matrix is an example of what we talked about before, where your b1 is e1 and your b2 is e2 up to bn equals en. So we augment A by b1 through bn, in this case it's e1 through en, that's the identity matrix, and then you row reduce, and then once you row reduce, you're going to get, well, you can tell if A is invertible or not, but if A is invertible, what you're going to get is you're going to get the identity matrix on the left, and then you're going to get A inverse on the right, because this matrix is what you need. The first column, when you do A times the first column of A inverse, you should get the first column of the identity matrix, and so on for the other columns. So that's how you find the inverse. That's the algorithm, and this is why it works. Okay, thanks for watching.